place is to be on the printer. Yeah, city center. No idea.
Okay. It's good if I'm in the same space as you guys are. Yeah. So this is how your lectures are made. I'll tell you some more about that later on. But it's yeah, I'll tell you more about the course in this introductory thing. But I just wanted to show you the kind of madness that goes on behind the production here. So I've been building this course for about 6 or 7 years, and I'm trying to make it better all the time. It's kind of an online textbook thing. So you should be able to come back to this at any point in the future, and it'll be the version you guys saw, or a better version, certainly a better version, waiting around, right? So it's no textbooks to buy, sort of thing, really available online. All right. Okay, so can I show you this first? This is all right. So I'm Peter Dodds. I tweet. So I'm going to ask that. We'll occasionally talk about tweets because I like social stuff as well. All right. So yeah. So this is principles of complex systems. I'll probably repeat myself a lot. I do that. Trauma. Anyway, you can stop me when I'm telling you stories again. So there are really 2 courses here. There's this course and then complex networks, which usually this runs in the fall, and then complex networks is in the spring. They go together. I was on sabbatical, sort of, last semester, which meant that I actually stayed here and did lots of admin. And I was very sad about myself. So, and I haven't actually taught for a year, so I'm a little upset. But I did love it. So, let's see. So, I'm going to give you, in the next couple of days, sort of a big story behind complexity. We'll keep coming back to it as we go through. It's going to be a mixture, this course, of analytical work, where we figure out mechanisms for how micro to macro transitions happen. I'll elaborate on all this as we go along. We're going to look at really just science as well. Like how do we do science today? It's been a bit of a rough time for a bunch of scientists out there trying to cope with this new data-rich world. But it's a fantastic time to do science. It's really one big thing I want to do. It's a great time to be building, designing, doing all sorts of things. You all know that, and it really is an amazing time. In 2000, there was a book that came out that said, "The End of Science." It's a fellow German book. Gone, right? It's done. We figured everything out. People say this all the time, but it gets more and more fiction. Okay. So humility is a good thing. All right. So let's see. So today, it's going to be a little bit of orientation to start with, just some stuff about the course. I'll give you sort of an overview of topics in which I won't talk too much. Then we have projects in this course, so I'll talk about that too. What I looked there. There are assignments and projects. A few pointers to a few things like popular books and more serious books that you might want to look at, for your own interest. I'll give you some sort of details behind these things. I should say that, well, let me add this. So my background is physics, really, math and physics, and accidentally electrical engineering. Right? So I'm from Australia. I went through what's typical of outside the US, where you come out of high school and you become a doctor, or you go straight into those things. So I did a 6-year undergrad, which I sort of forgot about until recently. I was thinking about this, but I did 6 years of pure math and physics and engineering all the time, because it was 2 4-year degrees, apparently, the one delightful 6-year period. And I did one non-science thing, and I did a history of structural English language, which was possibly my favorite course in all of that. So I didn't know what I was doing, obviously. I was just taking more and more science stuff. And then I did my PhD at MIT in math, but I was really in earth sciences, working on networks, actually. So that's going to be a big part of this course. Like I've written it, because it's a big data story. It's where we are now. Find yourself there. Okay. Let's see. So I spent 6 years there. And I came to I'll tell you this, I came to the US to work on complexity, right? This is the big story when I was coming out of college. Then I spent 6 years at the Social Sciences Institute at Columbia. So I am one of these hybrid human beings. I suffered greatly in making my brain, add more things to it, and just becoming immersed in that world and the social sciences world. I'm now in math here, but I'm not really. I've never published on math paper. So I'm really kind of a physicist by background, I suppose. I'll tell you more about what that means later. So that's just to give you an idea of what I am. All right, so I'll talk about all these things, and then I'll give you this overview of the whole story, right? Complexity, there'll be a manifesto in here. These terms, emergence, self-organization, this is a big one, of course, emergence. What we're really doing when we're tackling these problems. Is there a theory of complex systems? What's the best way to view this? Should you be just a theory-producing machine? Should you look at things? This is really an amazing battle that's happening now. Should you just look at data? Should you go out and just look at things? And actually, the answer is yes. This is what real science is. That's a little hard for people to understand. Okay, so I have a couple of girls, and these are some of the team members. So the most important team members. So we have new producers on board for this series of project. Good guys. All right. We lose them. We'll be back. So I said I'm in the math department here. I'm also really in the Complex Systems Center. I'm the director of that, and somehow the chair of this Complex Systems Spire. So we have these two things which are sort of the same, but they're not. So, all right, lots of complex systems. And then within that, Chris Danforth and I run this group, which we call the Computational Story Lab, which is we're very into framing. This is very much something we're going to study. That's what we think. I think everything's about stories, actually. I think equations are stories. I think human stories are stories, of course, and it's all connected. All right, so these are some of our team members. Some of them are here. We've had a few alums. So Chris and I have been here for about 6 years now. People have moved on to all sorts of different positions, and I'll come back to this. But one of the nice things about the work we've done here, of course, with the group, and it is a research group, but also these courses that I have here, is we've had very direct academic output. So papers coming out that have done well with many of these guys as lead authors or co-authors. So that's, if you're a graduate student, this is a good thing to be thinking about. All right, this is the guy I work with, just so you're clear about that. I know some of you actually done this race. This is the Spartan race. This is towards the end of the video. I do I prefer very nice, clean ones, triathlons on road surfaces. Yeah, so, anyway, Danforth. All right, so more about my little history. I really like figures, so these are little pieces from each paper. I think you can click on these. You actually go to the paper, but you can see how it's all about river networks to start with. This is actually about trees, so how trees grow in forests and how they pack together because they have this nice distribution of sizes. There was a real problem there. Then we went and started packing all sorts of funny little shapes together. I remember doing the calculations for that while waiting to see Urinetown on Broadway. It's best to be in strange places to think about things. This is something I talk about a lot in this course early on with scaling. So we're doing a lot of stuff about system scaling. It's actually about, this is biology, so these are the size of mammals this way, and this is their resting metabolic rate this way. Right? So there's this great problem as to how that scales. Right? There's these double log things. So it's a very controversial subject. Some of the guys behind some parts of it should go on over it, actually, probably say some things to over. If they want, well, maybe they will. So very controversial. So then there's all sorts of stuff here about spreading. This is all contagion stuff. So there's a little TV in the middle. This is about influential stuff being spread. There's stuff down here more recently about happiness. So we're trying to measure happiness from Twitter, trying to measure happiness from large amounts of data. I think that might be sort of a final lecture for this. So lots of stuff about spreading contagion. This is about success. This is an online experiment. I will talk a bit about that towards the end. I can't help myself. I will merge my work in here because it's part of the story. And the small world network story. So I'll tell you about that. The idea that of 6 degrees of separation, people aren't very far away from each other if you look at the whole social network of the world. And that's been very popular, very exciting. It has real world implications of how you deal with information and data, how you think about search. So lots of different things, just to give you a sample. All right, so there's going to be some boring things. So we live over on, in Farrell Hall, so that's where we have our office hours. There's a course website, yes, right. So that's a sort of building and repurposing, right? So here's our course website. You'll see here, so this is the slides from lectures, for example, so what's going to appear. I'll tell you this again, I'll have another slide of this, but these lecture slides will be these guys. These are the ones with all the little reveals and the little fancy bits. There's a handout, which is looks like this. If you really want to kill some trees, you can print out versions of the slides that just put into 3x2. I did that because I could, possibly. And what else is on the website? The website's full of goodies. Academic output. So I need to add to this. We have about 12 or 15 papers now. These are papers that have come out of work in this course. Right, course home, blah, 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 stuff. But the lectures will appear here. And so, as I said, right, so the lecture is the thing I'm showing you now. The handout is that little, we went to the slides, it's just a flattened version, so you don't have all the little reveals every time you go to a new slide. Today is about, this one's about 100 megs, so it's a little bit, sorry about that. So this was a compiling before. Yeah. Anyway, trying to make a product, trying to get it better. And you will presumably help me, as team members always do in these groups, by saying things are wrong or whatever. Anyway, this is Vote. Oh, no, not Vote. So this is a horrible problem. I have to fix it. We're in a slightly better place, actually. Yeah, voting is one of those crimes against humanity that occurred in the 60s in an architectural sense, and everything should be just start again. It's really bad. Happened all around the world. Don't know what was going on. But you can see what the engineers are also probably just architecturally destroyed. No other reason. Let's see. So there's a syllabus that I posted. Download those things, print them out, put them on the wall. Office hours are probably going to be on a Wednesday. Usually the assignments we have in here tend out to be challenging, right? So I'm not going to give you all of the tools you need to do exactly every problem. So this is a bit of a bridge between here's how you do something, now I'll give you something slightly different and you do it, right? That's calculus and all these things. Yeah, we're getting more research. Right? So you'll actually go through some of the classic problems that people solve. Some of this stretches back certainly to the 1950s. Some foundational work back then by all sorts of famous people, and you'll be tackling their work. Some guys like Herbert Simon, who's a Nobel laureate, and a lot actually contributes to some of this other faculty. Okay, so this is part of a graduate certificate course. There are it's a 5-course requirement. It's a good thing to sign up for because we're a crazy graduate college and I don't know what this is, but they sort of get upset if you do it before and not tell them. I don't know. So it's a good thing to have. You should sign up. It's tricky if you're an undergrad, I don't know. Okay, but this is Maggie Epstein is the person to contact here. So this is one of the 2 required ones. This course, Maggie's course, is about modeling complex systems. So you have a little MATLAB frenzy and maybe NetLogo and some other stuff and build some things. So these things join together. And then there's a sequel of this course, POX, which is not a very good term. But there it is. Didn't think of it. POX. So, complex networks. Which I told you about. All right. Good. Having fun. I told you about these things, right? Right, about this. If you play around with these things, there are little backwards and forwards things, and there's a little find. So, it's all a built-in hypertext thing, so that's a little search thing. There'll be web links. I'm trying to make this thing exist, rather than be a little bit of dead tree. Right? Click out to things. I'm quite happy about the Wikipedia. Things will be clicked to. Another bonus in JSTOR, who can kind of jump on themselves because they're sort of bad. The JSTOR, I don't know if you've heard of them, it's a journal repository. I mean, it's a good thing in principle. They've been bringing papers up from old journals for a long time and storing them online. Of course, you have to be part of a large institution to access them, generally speaking. And they complain because I have, some of my papers are reachable. Some of the papers I've stored, I have several thousand journal papers stored underneath all of this, that if you link to them, so for example, this should work. Of course, it won't. We'll talk about it. If you click on this, it goes to the end, and there's the paper, right? So you can click on this, and it will bring up the PDF, which is good. But it's the original PDF. So this is the thing. This course that I'm giving you is connected to the original research. And right, so it's all in these references at the end. The problem with JSTOR that I was trying to talk about is that, yeah, they wrote to UVM and said you shouldn't have all these papers. So I'm trying to make it so that Google can't find them, which is what happened. Google came in and rummaged around in my drawer instead. Thank you, Google. And it's, you can't do it with directory. It's not an open directory. You have to be able to go to it. So of course they went through these PDFs and found the links. Okay. There will be links to PDFs. Some books will be linked to Amazon. Money, I just like to do that because I'm kind of insane. This is what's underneath all of this. There's LaTeX and Beamer is the slide pen. This is very good. Perl tech. So actually this is Perl, which is a scripting language if you don't know about it. It's a beautiful, magical, crazy, natural language kind of thing that people hate in general. But I love because it's more human. It allows you to do all sorts of things with text. But there's Perl inside LaTeX wrapped in Perl that brings you this course. So it's the Enigma in the wrapped in all those things. All right. And Emacs. So this is super packed. All right. So we can do lots of things. Scripting is greatness. All right. More about the course. So projects and talks. So there'll be 36% for this. I'm going to give you a first talk, a last talk, which will be an exam period. Now, there are a lot of you in here, which is good. And I don't feel want to leave, but try to make that happen, which is a very natural professor technique. Right? Try to turn it on in the first couple of weeks to make sure that numbers go down so they don't have to work too hard. Not one of those people. But these talks are short, actually. The first ones are sort of maybe 3 minutes long, which sounds like that's terrific, but that's actually pretty hard because you have to get it done, otherwise you get the gun. That'll be about what you're working on, right? So it's actually it's like a little conference, mini conference. In statistical mechanics, which is a physics area, which I'll talk about. This is we use quite a lot. We have these little 3-minute talks, someplace 30-second talks, just to help you get through all sorts of stuff, and I think it gives you a nice little test. All right, and then we'll have the final talks, depending on the team members. We'll have to figure out how to do that. But it will be the final exam period. This adds up, yeah. So assignments, yes. Maybe 6 or 7 of these things. Usually there's some teamwork involved, which is probably good, and suffering, which is also good. So that's good, fine. I want you to really actually go and work in a box by yourself. You should do that as much as you can, but you need to probably talk to each other for this one. Okay, that's the plan. This is how I grade, actually. All questions are like this, and it works pretty well. So you have a very long question, and you just end up with 0, 1, 2, or 3, but it averages out very nicely, so just so you know. More things. They're not more, they're important things. That's a little boring. But we have 27 lectures. I'm going to email you things. Access, of course, you can see me or send me an email. I love email. I love terrible email, but I will respond to you. Okay. Okay, so this, good. What are the topics? Okay, so let's start to talk about the course. So I'm going to tell you these things, one page, complexity manifesto. What I've come to see is the story of complexity. There's this essential point that's basically now becoming normal science. Right? We have being able to measure in details the elements of systems. To an extraordinary degree, and it's going to keep going until we've opened up the box. A lot of biology equal to a large extent. And of course, we're putting ourselves on the line more and more, so we get this great insight into social systems. We have satellites. I mean, it's crazy. It's crazy amounts of data. A great example here is astrophysics, right? Which in 2000 transitioned from being a scarce data area to a rich data area. So it's all these. There's planning, design went into it. The bank, it's a real base transition. It used to be that you'd go to your, you go out to a telescope somewhere in Hawaii, which is quite nice. If But if it's cloudy, you know, for a couple of weeks there, you're in a bit of trouble, and bad things could happen, it might not work out. So the kind of skill sets you need then, a lot more theorizing, right? So when data's not around, theories balloon. And that's kind of fun to watch those areas. But philosophy, if you ever look at a lot of philosophers, you know, get into they pretty much say anything, right? They don't constrain themselves by reality. Reality is a real problem, actually. You have a beautiful theory, you get into a lot of trouble when you go test it. So we're all about testing things and seeing if it's true. We'll talk about that some more, right? So this is a data theory and experiment. And really you want all of these things working together. And a bit later, maybe on Thursday, I'll show you a ridiculous example involving cats lapping milk, which is, you want these three things matching up. And certain areas, you know, really maybe only have this, maybe they only have this. It's about, but you need to have all of those things. This idea of emergence, right? So you, so maybe you can think of the financial system writ large, right? There are dollar bills running around, but the properties of the financial system are very different to an individual piece of paper running around, right? Atoms, of course, the humans, you know, whatever you like. I'll give you some more examples of that. But it's this idea that not just the whole is greater than the sum of the parts, that's sort of but it's also fundamentally different, right? They're qualitatively different in behavior. Two huge pieces here. One is universality. This is a term that comes from physics. Physicists, of course, thought they would explain everything in the world. They're still trying to do that by blowing things up. But physicists really run into trouble when we go up through scale, because we end up with horrible things like DNA, and more likely, and it's a hard problem, but accidents of history. Right? How many fingers you have, maybe. There's some arguments for why you should have 5 or 6 or 7 as a result of things growing and so on. There's all sorts of ideas about explaining why we have certain structures in the world, but there's certainly a big part of this is path dependence, building on top of what's come before. But universality and path dependence, if you like, can go back hand in hand. Right? So you can have the global behavior of, say, people has some particular signature to it that would emerge if we were talking about octopuses. Right? You get that same global behavior. Always good to think about octopuses. Really helpful. Okay, so structure and stories, right? So we're interested in the structure and the stories of how those structures came to be and what happens on top of those structures, particularly networks. Networks are a huge piece, but this micro to macro mechanism, so that's something that we've been very successful with in physics, right? So explaining what the gas in this room is in a certain way, by thinking about molecules interacting and doing that in a statistical way. That's a pretty extraordinary success, right? And fluid mechanics is another amazing success. We've described an enormous number of things with how we use those equations. Unreal. It's unreal. Right? It could be that the equations that describe honey and blood and water are all different. There's something, fundamentally different about them, different derivatives and so on. But it's really actually just parameters, right? Viscosity. They're the things you can measure, or temperature, so you can measure those things and put them in and make some approximations. And these are magical equations applied to lots of things. So that gives us hope. That sort of thing gives us hope that we might be able to describe many more things going on, but it's just been harder to get there. So in a sense, physicists have been able to get at the easy stuff, right? The measurable stuff. More things are coming online as being measurable, and we're seeing how far we can go with these beautiful theories. I'll have a nice piece later on, so I might have a piece later on that gets at some of the horribleness that we might get into eventually, where some systems are just inherently complex and there are no simple math equations to explain. That's, maybe we're in a bit of a period where we can do that. We have this crazy math stuff that works. Of course, we move beyond math to algorithms, and that's really where the big stuff is. So, some elements. There's always the element of surprise. The scaling, surprise, so but that is a big statistical surprise, right? Which is a fail, right? Suddenly we don't have a financial system, suddenly we have earthquakes, suddenly whatever it is, boom. A lot of complex systems have this property of robustness because, of course, they've gotten to a large size, they're big systems, and good, right? So we need to understand that failure. And there's this notion of, which we'll come to later on, Robust yet fragile. It's like you're an Achilles heel in a system. So it gets tweaked in a certain way, the whole thing comes down. So a blackout of maybe 2003. The reasons for that are still being sorted out. It wasn't a big thing. It wasn't sort of a big distributed attack where lots of trees fell down at the same time. It was a weird thing that happened to trigger a big series of events. So they're kind of triggering cascading failures. Big deal, consistent. And usually we find out about them by building a bigger system, which then collapses us. And then we make it better, and then we make a bigger system, and that collapses us. So we're kind of getting theory of anything. So this is like the theory of everything. Right? So some fundamental equations that describe the smallest particles, the emergence of them. But I think there's actually also this other adjacent story, which is likewise. So why do things just keep marching up in terms of complexity? I think you can answer that, but I think there are elements that we can kind of understand. Right? You get eventually, once you get to life through a bunch of ridiculous accidents, you're in an algorithm world, right? Life is algorithms. You've stepped out of raw, cold physics, fluid dynamics, or whatever it is, the basic fundamental forces of nature and gravity. So you've stepped out of that. You have a choice and some sort of craziness that happens with life. And then, of course, you get to games, evolution. Right? You get to sort of cooperative games and, of course, competitive games. It's been played out, and evolution takes place. So that, maybe I'll just explain it a little, but then, what happens as we go on? What are we going to get to the scale of the world with us connecting ourselves? Do we always come to the same place? All right, so a little more specific. So scale phenometry, other means other. So this is a measure of how different aspects of the system scale. So I mentioned this one of metabolism, the rate of energy used by organisms as a function of their size. You can do the same for engines. You can look at dimensions of organisms. You can look at the sizes of cities, actually, for example, and the and the productivity of that city, right, in terms of patterns, or average wealth, or crime, or disease. There are scaling laws for these things, what we call scaling laws. Scaling biology, platypusal feature, as it should. Very weird creature, of course. So mice to elephants is more of a reasonable transition. We'll talk about these things called power law size distributions, whatever that means. But that's the things that are describing wealth distributions, for example, earthquakes, and we'll get into that. We have some kind of idea in the general, of how these things work. That things like the 80-20 rule, for example, 80% have 20% of their wealth. So they're phrasing these, of getting a bit of a handle on these distributions. 20% of the people might have 8% of the wealth. That is just the tiniest glimpse of what these power law size distributions are like, but it's much more richer than that. And dealing with these things analytically, which you guys will do, will produce some suffering, but hopefully we'll get a handle on these things. They're incredibly different to Gaussian statistics, which there was a tremendous moment in mathematics and statistics figuring out the bell curve. It's really quite an extraordinary function, and the realization that this thing occurs everywhere, again, into universality property, is pretty amazing. But the ones that really worry us are these parallel size distributions. They're the ones where we have surprise. The statistics of surprise. At least that's what I call it. I have this thing called Zipf's law. So this goes back to the 1940s. This crazy guy, George Zipf, who was looking at, just kind of as we are today, looking at things like the number of cities of a certain size, and the frequency of words, frequency of usage of words and texts. Making registers to count things. All sorts of stuff. What was the number of marriages in Philadelphia as a function of the distance of the people lived apart in blocks? So he was on a bit of a rampage, and he published this magnum opus of his principle of least effort, which is basically sort of the Homer Simpson rule for humans. And it doesn't explain it. It's sort of a story, but it doesn't quite get it analytically. He has all this data and knowledge of it. And then I think he passed away the next year, so I don't know too much about it. I can tell you a lot about many of the other characters involved here. So quite good thing. I'll give you some dirt. But this guy's a bit of a mystery. Anyway, people talk about zips a lot. And again, so this idea of a mechanism, right? So what gives rise to these structures, these very unusual structures, which they're unusual in a sense. So say, for example, in statistical mechanics, wrote a possible but very unusual status for all the molecules in this room to be in that top corner. We do this analytically. We say that is equally likely as having the arrangement that we have right now. It's just that there are so many arrangements right now that they give you the kind of macro form we have now that this went. But what we see with networks and a lot of these real structures is that we actually get that weird configuration over and over again because it's built. Networks grow, and they grow in particular ways. Wealth grows, whatever it is. So this is a lot about scaling. Okay, lots of systems have these scaling features. Complex networks, just to tell you, right, this is a huge transition once in this whole complex systems story. We're trying to figure out complexity. It's out there, it's obvious, right, but it's complex. Lots of discussion and talk that went on for many, many years, and it was a good frame. Right? It was a very good frame. It's a good frame. But the realization that many of these systems have networks underlying them, and really what happened is that we could measure them. Right? We started to measure them, we started to put these big data sets together. If you look at, say, social network theory, going back before the 90s, you have people going into, say, school and measuring who's talking to accounting for who's talking to who. And you know, they're great studies, and they should not go away. That. But now we have, of course, deepest data sets from, say, Twitter and Facebook. They give us some other insight into how people connect, but we just never had before. All right, so that's, I'll say it again. There's this data transition. We went from not much to a lot. And there are these two big, well, there's random networks is a big deal, and that's good fun. Scale-free networks is a huge thing. So again, this is a scaling story. In a bit of a weird way. This is Laszlo Barabazi, who's obviously small world networks. This stuff that I've been connected with for a long time. Duncan Lutz and Steve Strogatz are the people behind this, and I worked with Duncan for quite a while. We'll hear more from Strogatz and about him. Okay, so lots of stuff about networks. This is the family stuff I was talking about. This is very enjoyable theory, HOT, highly optimized tolerance. It was an attempt to make cold, but that was weird. But this is this robustness and fragility. It's a nice thing for people who think about evolution and engineering systems, that you're always trying to make them better in certain ways and trying to account for the environment producing bad things. So imagine you're a forest, and you only have so much money to allow you to create fire breaks. Where do you put them? Right? And you have some idea of where the lightning strikes out, or where the arsonists whatever it is. Let's say lightning strikes. And if it's really unevenly distributed, and you begin to kind of respond to that distribution, it's easy to create a system that's robust. You'll put fire breaks around the places where there are lots of lightning strikes. But you'll leave huge patches open where they very rarely happen. And then those rare ones will bite you. Make sure they don't happen, when they do, it's a disaster. So we'll see this in a number of different scenarios where, kind of toy models where we get at this idea of systems working very well for a long time and then going forward. Information language, lots of stuff in here. Knowledge, all sorts of things, we talk about that. Again, it's a data story, we'll be able to get language more and more. Particularly English language, you can see this evolution of rules that come along. Lots of interesting things in there. Lots of stuff with information. So search and network systems, so that, of course, it's partly Google, but also search and social systems, which is a bit of a harder thing. We'll come to that. What I call socio-technical systems, and I think we live in the socio-technicine of the opposite people and computers and infrastructure that make crazy things happen. Good and bad things, of course. We'll talk about contagion. Right? I don't know if you have the flu, but there's great work by Vespagnani that's kind of built out of years of complex systems type of modeling that's really becoming useful. Of course, you have crazy things like Google flu trends. Right? You can get a sense of when it's a spike, like people looking for the flu, and searching. People tend to be a little more honest when they search. Right? They say different things on Facebook, and when they search, they tend to be a little more quiet about what's going on. Lots of things. Cooperation, this has been an ongoing problem. Economists and sociologists and so on love this problem. Why does global cooperation emerge from? When I say bad actors, I mean economists, people who are selfish and rational, right? Which is their view. Love bashing, but also physicists. Okay, so, but I think you have this opposite story, which I think is actually much more of a dualist. Good actors cooperating, creating some holes, quite a nasty thing. So you have wars, of course, team sports, all sorts of stuff. Large corporations destroying other large corporations, or small people. Everyone's doing good things. All right. We'll look at that. Talk about cities, how people move around, there's lots of stuff. And hopefully, with some of the projects you guys work on, you'll be able to present some of the recent stuff that's going on here as well. There's some great stuff about groups and individuals based on cell phone data. Okay, this is some of the stuff we'll get to at the end. Voting. We have this idea that things win, and socially, and they win because they should. I'll tell you about some problems with that, and where the superstars come from. So that's something about voting, where it can go wrong. And this is an incredibly important thing, because we're doing it all the time. You always evaluate things. We're putting more and more online, and Amazon, Netflix, and so on, and small things, because we vote for presidents, we vote for all sorts of things. There's lots of systems where we're trying to get together people's opinions, markets, of course, fundamentally about the wisdom of the crowds. So there's a collective idiocy of the crowds as well. We want to know when that balance is going the wrong way or the right way. This is a sense of where we're going to go. There's a lot of stuff about scaling. We'll get onto this robustness of failure, the mechanisms for where these scaling laws come from. It's just a big deal. And it's sort of, over time, I've developed this. It's really a central thing that you guys just have to put in your hands. But there's just an infinite amount of stuff we can talk about when it comes to complexity. But these are really core things. There'll be a section on complex networks and then some stuff on social phenomena too. So that will be broadly the story. Okay? Right, I'm going to add this squirrel for some reason here, but I'll explain what this is later on. I get potatoes, so some people know this, but this is a synthesis of a bunch of different observations around social phenomena, spreading, influence, success. So I'm trying to upgrade these things, and that's where they kind of finalized. But I'm really making life this way. I'll explain that later. And then you can go off and become incredibly successful. All right, sure, secret. Projects. So the projects will work like this. So you want I'll talk about them next Tuesday. I'll give you sort of a fun thing for me to do, hopefully for you too. I'll just bang through a bunch of work that's been going on, some other things as well, but in the last, I'd say 10 years, and a bunch of papers. So if you're on the undergraduate end of the spectrum, then you might be wanting to just take a paper, really understand it, and present it to everyone else. And that's good. That's the key part of developing your research. If you're a graduate student, you may have a project in mind that you're already working on, or you can pick up on any of these things. You could talk about working on some of the stuff we do, and maybe try to develop that. Okay, so it's a range, all right? That's this novel research to something that's been done clearly. I mean, there's some, of course, this work is new, so you can propose it as well. But that's good. Mention this. All right, coding well superpowers. So not erroneous to code, but it's not essential for the course. The assignments will be analytical. It's a little bit of code, but it's not key to it. But of course, I'm happy to help you get onto this thing, the fact, what we call fact. Which is a good thing to have, I have to say. We have some large data sets. I've been collecting Twitter, for example, so it's just an enormous mass. I mean, it's like 10 billion tweets that we have now. I can't remember what that is. Which is about 100 billion very meaningful words. Of course, from Twitter you have interactions, so you have a sense of networks coming out of that. So we've been struggling with that stuff for a long time. We have lots of other data sets as well, but that's a big one we've been collecting. We've had it since 2008. We wrote to them when we had 4 people working there and said, this looks interesting. So it turns out now that we have something. Now we have something that's a little bit rare, actually, which we'd like to share. It's just can't put it on my thumb drive. Okay, we talked about the academic output. I'd be super thrilled to see, you guys produce papers that come out of this. All right, list of projects. I like this. This is a thing I've had for years. My wife's a journalist, and she showed me this little pyramid thing that she found in some magazine last year. But it was basically this, which I've been running around for a long time. So, if you have some story you want to tell, you need to be able to tell it on all scales. Especially, this is very important in academia because people tend to be down in this area, especially if you're a graduate student, which is fine. But you say, what are you working on? And about 3 hours later, you finish the synopsis. You do need to be able to produce at all scales. And it's really understanding. It's not just so you can talk to the press and funny. It's understanding, right? It's getting it down to a very simple story. So a friend of mine from years ago, Andrew Markoff, who's a brain surgeon now, which kind of terrifies me, is I remember years ago, and I'll mention him again, so I'm sort of mentioning him now. So I'm mentioning him because he actually turns out to be pivotal in my career development. He was doing medical rounds, right? So this is again in Australia, right? You go straight out of high school to becoming a doctor, you get terrified. The people in charge keep saying, what's medicine? What is medicine? And I kept getting it down to a soundbite. And they ended up with, and it's pretty blunt, it was pattern recognition. It was the distillation of what they were doing. Which is fine by me, I don't want to be a doctor, it's not good. But that was a good, it can be a real battle. You can be down here for a long time. Some things only live up in this space, and they're no good because you stack. You try to find me in more depth. Some things kind of only live down. All right. That was just my having fun. Oh yeah, so this is Mark, who has all of these things associated with him. If you know Terry Pratchett, that's a joke. Should be Terry Pratchett. So we talked about thaumatology, which is magic. Okay, so this is a book that Murray, my friend Murray, handed me in 1993 and said, chaos is pretty good, but look at this is great. So it was we were taking these courses on chaos theory, and it was fantastic. But this book appeared, and it's very much just about the characters involved. 7 or 8 people. It's the Santa Fe Institute, what is called the Santa Fe Institute, which has been put together in the 80s, and by Nobel laureates in economics and physics. Murray Gell-Mann, who's one of the maniacs behind the whole particle physics story, a theoretician, who came up with the word quark, is his quark, which should rhyme with something else, but it doesn't. I think it's from Finnegan's Wing. Anyway, he's pretty nuts. But they started this institute. It's Santa Fe, right? It's very nice. They're connected to Los Alamos, so there's people with brains running around. And one of the characters from there, Stu Kaufman, is now part of our team here at UVM, and is very well-known. He's not in any way retired, but sort of anyway, he's in this book, jumping out of hot tubs and running around saying Eureka and stuff like that. Right? So, but it was great. I read this and it was really interesting. These people were really tackling, trying to think about hard problems. And there's everything's in there. Things like seeing how birds flock together. You can't do that with differential equations. It's an algorithmic story that these local behaviors of birds. And this is still a huge area of research. Birds behaving locally, so they just look at some of the birds around them and try to adjust, and so on. You get beautiful flocking patterns. The computer will be very happy with yourself because it's special. That's, there was a lot of work that was going on around that, using computers, which is, of course, computers is pretty, the macroscope. I think there's work out, of course, the macroscope. Okay, this was a big deal for me. It's kind of a funny book now, but got me excited. So I came here and said to the UK. Now I went to MIT and beat it out. I said, no, I use it with fractal chaos, I said those things. This is for children. These links all and stuff like this. Neil Johnson is a friend of ours, friend of the show. He is down at Miami now because his wife is Colombian. He used to be in Oxford. He's got the modern family situation going on. He's just basically a little Englishman. Anyway, so he's got a nice book here if you want to pick up kind of a popular science one. Melanie Mitchell has one as well, so there are at least two I would recommend. Allied to all of this is Gleek's book here, Because You Wrote Chaos, which is this inspirational book for so many people who went into science, I think, the areas I'm in. This is a really engrossing read if you're into this kind of thing. It's great. So it's a little bit different to these, but these are two sort of popular science books. So Melanie Mitchell, I mentioned her again. She's running a MOOC, the massive online open course thing, whatever it is, through Santa Fe. No math, nothing. It's not like that. It's just complexities interesting. I'm going to show you lots of things. So they're doing that this year. If you want to look at that too, I don't think it's started, but it's there. This is a classic. You can now get it for $25. For a long time, you could only get it for $1,000. But now they made a reprint of it recently. $25. It's pretty interesting to read. It's pretty interesting to read. I mean, it's written in a funny tone. It's a long time ago. But the thinking is all right there. So this is a classic. This is a very famous book that many people will point to, and I'll bring showing up a few times. But famous for a lot of things. One of them is having a Nobel Prize, which he got in 2005. So he's been recognized. So he's an economist, but he's one of these people who sits there and really tries to think about what people like. Real people. Not economics, but real people. This is a so Phil Ball as an editor of Nature. Yeah, and so Nature and science are very different journals. The science is, we will make sure that scientists like this work. When you send anything off, and check it through a scientist. Nature has more of an editorial board, kind of like the Economist sort of thing. We don't like this, right? They make decisions and then they get it vetted by scientists, but they have an editorial board that really thinks about things. Anyway, so this guy sits there and gets all these interesting things coming across his desk for years and then writes books about it. He writes very nice books. This is really about physicists coming into the social sciences. Very, really interesting things. And it's 2004, I guess. So networks have happened, right? Books written before 2000 don't say anything about networks. And they're kind of silly. They're just missing, there's just this gaping hole in what they can kind of get a handle on. But this is great. There's a piece in here that I want to mention, I don't think I have anywhere else, which is he digs up this story that so people like Maxwell and Boltzmann, who were thinking about, who created statistical mechanics, right? So they're thinking about how, they've sorted out how to get this story of the gas here from thinking about little guys pumping into each other. And so they're living in a mechanical world, right? There's the 1800s, everything should have a nice little path there, and stuff like billiard balls. There are a lot of atoms and molecules and so on in the air. That's going to be a hard thing to work out. So they went to this, for physicists at the time, pretty ridiculous step was to say, well, let's look at it statistically. Let's imagine things randomly kind of moving around. We'll kind of give them a little more of it's not really what they're doing, but we'll give them this randomness. And their inspiration was from social phenomena, from the birth of statistics as a field studying people. Right? So this is really nice little connection back to social stuff. They became, I think, intrigued by the kind of patterns that people, essentially actuarial people, were finding for, let's say, insurance purposes. Right? How many people are going to be kicked to death by a donkey this year is similar to last year. Right? And they were good at it. And that's pretty awful for not existing, but it's a difficult problem. But they were able to do it, and they'd say, well, here are the statistics. We have this thing, we have some errors, and we have that little bit of thing. And so they were doing quite well in describing. So they took this sort of, okay, well, we're going to make our guys statistical, and our theory is statistical. It became statistical mechanics. Right? So mechanics should be all about balls moving around and hitting each other, and things going exactly where they should. Especially in that time, of course, chaos was sorted that out. But It's a big step. Anyway, there's a nice connection. And then eventually you have all these people that drain the life out of statistical mechanics. They think about magnets, everything, and just get as much as they can out of that one. There are still people in that field, of course. It's a big field, a little crazy. And then they come rampaging out and try to apply their techniques to lots of other areas. In some areas it's successful. Biology is really hard for physicists because it's full of horrible little algorithms. Biology is good. You have to find out what they are. So, but this is a fun one. Again, it's a lovely story. These are more textbook pieces. Miller and Page were at Michigan, which is a big complex system center. So this is complex adaptive systems, and it's really about social phenomena. Page has given a few talks here on diversity. He has a lot of work on diversity, giving better outputs of all sorts of systems, human systems. Sonnet, who's an ETH Zurich, one of those big characters. They all hate each other, the students all hate them. The great tradition of psychotic science. But he just produces an enormous amount. He's trying to predict when financial crashes will occur now. But he has, it's a bit of a grab bag. If you're interested in looking at more technical things, he's a real physicist. It's very cool. They build all over the place, but it's working stuff there. And I used to recommend this as a hope to have for this course, but just working it. So this is Prakara. This is actually now, I think it's a 2007 or 8 version of this. Modeling complex systems. Yeah, it's he's at Princeton. So this is again a sort of a bit of a grab bag. Right? These are just to show you what's in. So Melanie Mitchell, I mentioned this is a link to what will eventually, I believe, be this online course. Ladder Adamic. I want to say damage because I mean it was but it's Adamic. I guess she's quite excellent. She's at Michigan as well. So that's more networks. She does a lot of interesting things. She had a great paper recently on recipes, right? So if you so you go through, and there were a couple of competing works on this. You can go through food sites and get all the recipes and look at the ingredients, right? And compare, across large, compare them to other recipes and so on, and do all sorts of data mining and fun patterns. There were a couple of big stories. One was the Western meals usually have complementary things. You can see this in a big way, and the Eastern ones have conflicting ones, sweet and sour. Right? And that is really, you sort of know, but you can see it in a big picture where it creates something that looks very, you can see it. Very different from the West. And they found a nice thing which makes sense here, which was cooked. How much people liked food, liked a recipe was clearly correlated with how much was cooked. Right? So cooking. I mean, being able to, the whole fire thing was a big deal for people. And then being able to cook food, we were able to reduce things and get a lot more nutrients in one small piece. So I think there's always a just so revolutionary story, right? But then you have that we evolved to really like the smell of cooked food somehow. But we'll go for it, right? We'll do charred stuff on the side of the barbecue. We'll eat it in a flash. Interesting growth. All right, there are centers around the world now, all over the place. There's a big one at Northwestern. There's Michigan, like humans there. There's another. There's all sorts of stuff at Harvard and around through Boston, Northeastern. Lots of different places, and of course we have one too. Right. But for a long time it was these two, Nexi. So this guy Yanni Abaye, he runs this. Put him in a chance there. Sort of connected. A couple other things. This is a good thing to subscribe to, on Twitter or whatever you want to do. You can get emails, but this is an interesting. It's sort of the place around, I suppose. It's been going for a long time. And it's just a filter. It brings in some recent interesting work on complexity. There's this interesting fellow Shaluzi, who was at SFI for a long time. I'll have a few quotes from him because he's kind of a fun curmudgeon character. But I don't think he ever sleeps, but basically he just writes about everything. And so he's kind of, and he lives in complex systems. So he's a good critical fellow. And it's just not connected to anything, it's just his website. I will make money if you click on this, it's just out of control. All right. Okay. How are we doing? All right, so we'll have a little bit of a start here. I'm warming up. So, complex. All right, it's a good word. So, and that's important. It is a good framing. So there was previous efforts. There's systems theory. This is fair enough. What else? Just some of the framings from previous time. I think they were just sort of pre-big data era that made it a bit odd. Trying to think of some others. The complexity was just kind of the right word, and it really helped. And the right type of framings and some of the right problems. So it has a nice origin. I like origins of words. People will talk about this, or get out of the way, complicated versus complex. And so people like to say this, that you'll have this, that some things like watches and airplanes are complicated, right? Maybe eventually lots of pieces. I'm not sure about this distinction so much, but the idea is that complex is a little more surprising, and these ones are much more controlled and engineered. You know what you're doing. It's just going on in bits. But certainly this can happen with engineering systems. You can get to this highly robust, but they can be highly robust and not adaptable. But the ones that are adaptable, if you make them more complex, they can fail spectacularly. Right? So you do, certainly engineering results in complex, what we would call complex systems that have emergent behavior that's surprising, unsuspected, very different from the local behavior that you've seen before. And so the reason that you get something like power grids failing around is that you see what's happening. You have all these power grids, all these local power stations being built, and they're well controlled, they're well organized, and they've been connected for business reasons, all sorts of more different things going on at that larger scale. So I'm not going to say this, but people will also go for complex adaptive systems. But it's just, again, it's a framing it puts you into a different bucket, right? It says that we're looking at things that can evolve and change. So a complicated thing, a watch. In other words, you guys don't remember this, but a watch that's unstable and be blinded. It's a complicated thing. It's not going to evolve. Okay, kind of have these quotes. All right, I guess I have these quotes. So, and this is an important point. It's not a single theory, and it never will be. Right? So it never will be. So it's this. If you talk about complex systems, you're really talking about the problems. So they're the things we can describe them. Right? So we can describe the kinds of problems we can work on and that we're interested in. So they're ones where you have lots of little different parts and pieces that somehow combine through some sort of network of interactions to give you macroscopic behavior that's different, fundamentally different, qualitatively different. And so people get stuck on this, right? They want the theory. They want to say there's a complex systems theory, but it's what you're working on. It's the field, it's the kinds of problems you're working on that defines complex systems. Again, same story. No universal solution. Well, this is about complex systems, right? But this is reasonable, right? I'll give you one that I think is okay. Connected agents that exhibit an emergent but global behavior not imposed by central control. So that's really important. It's not central. And the game is over as soon as you have enough central control because the thing is being made. But resulting from the local interactions, or somewhat local interactions between agents. And controlling it globally, sure. Right, again, complexity theory seeks to understand how order and stability, and of course, I should say, destruction, arise from interactions of many components according to useful rules. And there's Cosmo, he's always fun. So science, so he's got science and complexity very much in potpourri, and while the name has some justification, chaotic motion seems more complicated than harmonic oscillation things. I think the fact that it is more dignified than neat, non-linear nonsense has not been the least reason for its success. That opinion wasn't exactly changed by looking at the same things. So he's got it wrong. It's a framing. That's an important thing. And that's what happens with knowledge, right? We start to say there's this thing called biology. I'll show you a thing later on, but we didn't have the term scientist until 1830 or 40. We used that term. Just didn't happen. It was made up. I thought it was. Strogates. Some strogates. So these are bumpy ones. Every decade you have a grandiose theory. You won't know any of these that often have a C name. So there was cybernetics. when I was trying to think, that's a terrible name. Especially now, it sounds like you're calling cyborgs. So that's just a bad term. There are incredible people behind this. Noble laureates, also great people. But they just messed it up with the word. There are other problems. The 70s was catastrophe theory, which sounds great. It's great. I mean, that's a good frame. It was a catastrophe. So it was very mathematical. It was this idea that there was sort of separate. Yeah. So it's gone. Chaos theory is a big deal. So chaos theory is great, but it's part of a much bigger thing, which is dynamical systems, and that's incredibly important. And it was a fundamental realization about how systems work is that you can get this from entirely deterministic systems. You get fundamental unpredictability, which is crazy. And there's randomness everywhere. So chaos is complexity theory in the numbers, but it's time. In these sense, framed around complex systems. You see it all the time in the press. That's the complex system. Doesn't mean it's easy. You kind of got to frame. Okay. So here you go. This is not that. So it's a distributed system of many interrelated, probably network parts with no centralized control exhibiting emergent behavior. And this is this notion of more is different. So I encourage you to read this paper. It gets a little funny in the middle. I don't know if I can get this. So you can go grab this guy. This is from JSTOR, that guy. More is different. He's a physicist, but basically he's getting there and he's saying to these physicist pals that I'll come back to this later on. What was this drawing? Oh, he doesn't say it. I have a picture of it. It's just a little thought piece, really. But he's basically telling the rest of the physicists that they're not the ones who are really doing the only fundamental science, which was kind of the idea. Everyone else is doing applied science. It doesn't matter, nuclear physicists. Of course, everyone are sociologists, and they're just doing applied stuff. Right? So I'll have a slide about that. But it was a call to arms to say, no, you get the game that arises at higher levels, right? So now we have DNA, and there are certain things that can happen. We could have had all sorts of other structures, but we have DNA. That's it. And it's got 4 things on it, right? So there's a game that played out on that you're not going to describe from any fundamental description of physics. You can't go from balls to this. Some accidents of history that got you to this game up here, and you have to play. You have to understand the game. And so the theory there is fundamental, specific to where we are, what evolution produced for us, and it's just as interesting, just as important. Some of these things you might, contagion and spreading, for example, social contagion, social spreading, that probably works for octopuses, although they're not very social, they eat each other. But if you have any big social organism that can communicate, and they have iPhones and stuff, you should be able to apply that kind of theory as well. So there is a big universality. So that's more is different. So that term, that frame, right, that was the little buzz frame, the soundbite. Many people in this area, this field will point back to that, especially the physicists. Because he slapped them around a little bit and said, you guys aren't as good as you think you are. And I am one of them. And I'm smarter than all of you because I have the Nobel Prize. So there's a few other things you might see. So there'll be some explicit nonlinear relationships. It doesn't have to be. It could be the nonlinearity somehow sort of in the network, or it's not inherently obvious, but you can have little nonlinear stuff in there. Feedback loops. This idea of openness that somehow the system is being driven. Memory is a big deal, of course, because it's social systems. And this is a big deal. So many systems have some kind of hierarchical structure when you really look at them. There's some modularity, right? Just trying to figure that out is an incredibly difficult problem that's still going on. Papers with thousands of citations that build this kind of whole literature now on what's called community detection, which sounds a little bit benign, but it's really about finding. Here's this massive data set that's telling you about who's connected to who. If you plotted that network, it would be just a huge, horrible hairball. There's no way you can see anything. So you need some clever algorithm to go in and tease things apart. You're never going to do it by hand. You're never going to look at these things. So, all right, complex systems. everything, right? So brain, social insects, geophysical systems, the web, and color, right? I mean, just there are many, many, many complex systems that all have different stories. Basically everything that's interesting, and all the fields are involved. All of these fields have, you know, whether they like it or not, they're definitely into complex systems. I mean, of course, biology's been an amazing example. I talked about astrophysics, but biology's been an incredible example. Right? We've gone from thinking about the humus of the body, or phonology, and all that. These were big deals 100 years ago. I mean, it really was, absolutely was. To knowing what's going on inside, and it's really hard, right? It's really hard what we do. So, I think I should go to finish with the little manifesto thing that I have, which is just one page. Let's look at, so this connects to this little transitions in science. If you look back, so you have Democritus, about 400, saying, I think the whole thing's made out of atoms, right? Plato wanted to burn everything he'd ever written, they thought it was insane. I guess he had a few pals, but that's where it comes from. It's a very old notion. So A is not, of course, to cut, right? So you can't, these are indivisible small pieces that make up bigger things we'll see. So the notion was out there. It took us a couple of thousand years to kind of back that one up, right? So you have chemists going berserk, exploding buildings and being shot out of chimneys and all sorts of things that happened to them while they were doing that. It's called alchemy over the weekend. Who started to sort of get at this idea that there are these whole things. But it took us a while. It actually took us until this guy, Einstein, until we really were sure that there were atoms. We were really sure about it. So there's these two papers actually. So in 1905, he had a bit of a bumper year. There were 5 things that came out, and one of them was about Brownian motion. It was a statistical theory that showed how randomly bumping things is what's going on, and it made sense if you thought about these smaller particles. Right? So the atomic model gave rise to diffusion, which is just a universal phenomenon in all sorts of systems. Right? So again, it's like Gaussian, so nice Gaussian that spreads out over time. And that you could go from atoms to this nice big diffusing story. All right, so he has this paper, but this is 1905. And then in 1908, we have an experimental theory that experimental work that verifies it. Right? So now it's done. So you have people like Boltzmann, who was arguing with all his German colleagues, saying, no, there were atoms, and Boltzmann. He was a depressed kind of guy, but I mean, really struggled, brilliant people really struggled with this idea of whether there is essentially at some point indivisible pieces. Of course, now we know that it walks, all sorts of madness which we possibly invented by just smashing things together. Anyway, we've only known about the atoms since the early 1900s. I mean, only been absolutely sure about it. And we can start to, we're filling in the periodic table for one time, and all that sort of stuff, but now we're good. And we get to DNA in the 50s, right? It is. And that's pretty recent. So we've been figuring out what I'm trying to say here. So we had, I'll say it again. So this is the thing. So systems are everywhere. They matter, of course. They matter incredibly. Much of science is going to be about how, the long-term science, the long view of science is going to be understanding how things fit together. But we had to figure out what the things were first. We had to come up with words for them. So we've had this, in a sense, what I would call a golden age of reductions. And there's this kind of straw man silliness that you'll hear about saying, well, this theory is just reductionist. It's just crazy. I mean, we had to find out what the little bits were and put them together and understand how things work. So atoms, and then we go into particles and there's madness. And of course, there's this crazy time where people start predicting which ones you find, right? Which is really nuts. I think it was Dirac said, well, this is an electron, this is going to be a positron, so they found that next year. Dirac, who was an Englishman, also said that my equations explain all of chemistry. The rest is just stamp collecting. So, pretty much. It's not really true. I don't think you can explain people with these little equations. Genes, people, right? So when I say people, we're getting it out. It's a battle, but we're kind of getting out these reproducible kind of behaviors, ways that can be influenced, the ways we react to certain contexts and so on, and trying to be able to model them. So, understanding, of course, creating systems, which is a really huge part is design. And we have a nice project here at UVM on the smart grid story for power grids. Right? So you make up your new atoms. It's eventually the greater part of science and engineering. So that book I mentioned about in 2000, The End of Science, it's just exactly the wrong time to write that book. I mean, just the wrong time. I'll have another quote from a famous physicist who said the same thing about it's all over, we're done, right? Okay, so here's a big deal, universality. This term universality really means something to physicists. So in systems with quantitatively different micro details exhibit qualitatively similar macro. Right, so fluids, for example, they're governed by the same equations, but water molecules, air molecules, you get down to the small scale, like, well, this guy doesn't look like this. If you're thinking about just those tiny little parts, it might be unclear to the law, right, how they might behave macroscopically. But this idea of universality is very, very important. And the question is, how universal is universality? But it really is. And this is what's going on. So computing has made us, measurement instruments has made the science of complexity possible, right? So we can measure and record enormous amounts of data. Research areas, right? All these research areas are going from data scarce to data rich. Biology had this change, astrophysics had this change. Ecology, for example, is a bit of a difficult one, right? I mean, how do you observe food networks? You have to go out and get all the animals to turn up at the end of the day and say, I ate X, Y, and Z. I'm sorry, but I did it. So that's kind of a hard thing to remotely sense. So when you get to remote sensing, when you turn your subject into an all-knowing experiments, then you're recording. And we can, of course, so we're recording things, but we can simulate and model and do all sorts of crazy things with these computer systems, which are only going to get more powerful. But we've crossed the border, and now we can really get going. Yeah. So it's time to work on complex systems. It's a great area. It's changed since I started this course in 6 years. It's changed since I read that fucking book in 1993. We'll continue to do so, but it really, the network story I will say is the big one. It really changed things. So I like to talk. You like to stop talking, and it's now time to stop talking. But okay, so things are on the web. I will send you emails. There'll be all sorts of things. Wait. Oh my God. Hello, people. So I apologize because I've been waiting for about half an hour in Cody 205 because this is listed in 2 places. So just give me a second to set up, and we'll be good. So